Hello everyone. Let's begin with something you've definitely seen on TV or in real life. Picture a cricket match. The bowler runs up, delivers the ball, and on the screen you see the speed flashing 143 kilometers per hour. Incredible, right? Or imagine driving on a highway where a signboard warns you, speed limit 50 kilometers per hour. Why are such numbers important? Because they tell us how fast something is moving. This how fast is what physics calls the rate of motion or simply speed. So, how do we define speed? Speed is the distance an object travels in one unit of time. In symbols, speed equals distance divided by time. Mathematically, speed equals s divided by t, where s is distance traveled and t is time taken. The c unit is meter per second. But in daily life, we often use kilometers per hour, like cars or speed signs. Remember, speed is a scalar quantity. That means it tells us how fast, but not in which direction. And because actual speeds can vary, we usually talk about average speed. Let's take a simple example. Suppose a car covers 100 kilometers in 2 hours. On average, its speed is 50 kilometers per hour. Now, does this mean the driver was always driving at exactly 50? Not at all. Sometimes faster, sometimes slower, but overall, the ratio of total distance to total time is 50. This is what average speed gives us, a big picture summary, while the speedometer in your car shows the instantaneous speed at any given moment. Speed alone isn't always enough. To describe motion fully, we also need direction. That's where velocity comes in. Velocity is speed in a given direction. For example, if you drive north at 60 kilometers per hour, your velocity is 60 kilometers per hour north. If you turn east at the same speed, your velocity changes even though your speed is the same. So velocity is a vector quantity. It has both magnitude and direction. This simple twist makes velocity much more powerful than speed. Now let's refine it further. If an object changes its velocity at a uniform rate, we can calculate its average velocity as the arithmetic mean of its initial and final velocities. Mathematically, average velocity equals open bracket u plus v close bracket divided by 2, where u is the initial velocity and v is the final velocity. This formula works beautifully in uniformly accelerated straight-line motion, like a car steadily increasing speed or a ball dropped under gravity. Here's a classic problem. Usha swims in a 90-meter pool. In 1 minute, she swims forward 90 meters and then back 90 meters. That's a total distance of 180 meters. Her average speed is total distance divided by total time. So, 180 divided by 60 gives 3 meters per second. But what about average velocity? Her starting point and ending point are the same. That means her displacement is 0. And since velocity equals displacement divided by time, her average velocity is also 0. So here's the takeaway. Speed and velocity may give completely different answers depending on the displacement. That's the power of direction in physics. Let's wrap this up. Speed tells us how fast an object is moving, while average speed gives the total distance over total time. Velocity goes a step further by adding direction, making it a vector. And average velocity, under uniform acceleration, is simply the mean of initial and final velocities. Everyday life is full of examples: cricket bowlers, cars on highways, swimmers in pools. So to sum up, the rate of motion gives us a bridge between raw movement and precise physics. In the next lesson, we'll go deeper into how velocity changes with time, the concept of acceleration. See you in the next session.